Quantum conductance. It's how we quantify quantum point contact when it comes to conductance. What the heck does that mean? Why the heck is this thing here? And it's got a zeta. You all know what that means. We conjecture
Although
ahead.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So yes, we're back. It's a wee bit later and everything. We can see we have some quantum interference because I like to wear yellow and we got a green screen here. These things happen. But all right, what the heck are we talking about today? Today we're going to be talking about quantum conductance quantum. Yes. We'll get into the other things that I'm confusing with later. But all I know right now is what the heck is this? Basically, it's G naught here. It's the G Sub-Zero. Yes, it's not a fusion between Godzilla and Sub-Zero. Although I think they had an Evangelion episode where there was a snow Godzilla. But that's aside the point. All right. Here's our friend Wikipedia. Again, take it for what it's worth. Links to all the stuff and things in the doobly-doo below. All right. The conductance quantum, denoted by the symbol G0, is the quantized unit of electrical conductance. It is defined by the elementary charge E and the Planck constant H. This G0 equals 2E squared divided by H. So basically, we got two elementary charges squared, and then we divide it by Planck's constant, which is basically the quantum unit of action. All right, and that comes out to be this number here over there. But so the number we would be looking for, we'll go to our friend, and again, this is what it's based upon. This is why we have the little note right here. Okay, according to our friends at NIST, the numerical value we're looking for is 7.748091,729 exactly times 10 to the negative 5. When I saw this, I'm like, seconds? That seems kind of weird. Basically, the equation that I'm looking at for that, yeah, it's got a lot more than just the Planck boundary of time there. That might be a little misleading. So I went to my friend Wolfram Alpha and then double checked in the sources and everything. But where are we? That's actually a unit known as the Siemens, right there. As you can see, we have Siemens, micro Siemens, millisiemens, Ab Siemens, status Siemens. Basically, you look at the dimensions right there. What are we looking for? It's mass to the negative one. Basically, the negatives are what we are dividing by. And anything positive would just be the numerator. That's kind of how it goes. And we'll see that in just a moment. So we're looking for mass to the negative 1, length to the negative 2, time cubed, note that, and then current squared. Cool. All right. So we go back over here just for a little bit more stuff and things, because a lot of these different constants, the relationships between each other. But why are they a relationship? And we can infer, we can kind of go. But the whole point of like this project is like to tell a story about like what's actually going on in a geometric manner. That's the whole point, like the hyperbolic vortex equation, because the claim is, and again, it's conjecture, but the hyperbolic vortex equation can help us solve for the fine structure constant. Maybe we'll actually figure out why this dang number pops up everywhere. Oh yeah, it also has three sisters. But it appears when measuring the conductance of a quantum point contact, and more generally, is a key component of the Landau formula. The Landau formula, named after Rolf Landau, first suggested its prototype in 1957. It's a formula relaying electrical resistance of a quantum conductor to its scattering properties of the conductor. think that has something to do with like the Wayne displacement law and stuff. We did a video on that a little while back. All right. Which relates electrical conductance of a quantum conductor to its quantum properties. It's twice the reciprocal of the von Klitzing constant. Yeah, basically the von Klitzing constant links us right back here. Oh no, it's something different. Version of the it's a quantized version of the Hall effect, which is observed in two-dimensional electron systems subjected to low temperatures and strong magnetic fields. Okay, have we done a video on that yet? I don't think so. It's okay. It's okay. We'll get into it at some point. Hey, Dad, man. Thank you for joining, my friend. We're just going over a wee bit of the history of some of the constants in nature, in this case, chemistry and everything. At least it's from the chemistry poster that Dad sent me. So we pop back over here. So how the heck are we going to solve this? Okay. So that G naught, that's the thingy we were seeing right there. Okay. So in this geometric formulation, again, we're using what's known as the universal binomial factorization equation. What the heck is that? You have a primary action times your boundary conditions, which are basically the dimensional ingredients. And we happen to pretty much have 5 primary ones, and then mass, you could use mass, electron, proton, yada, yada, yada. So basically, the 5-dimensional ingredients are time, space, mass, charge, and temperature. That seems very interesting that there happen to be 5. This is something that you learn, and I learned from Thad, that you spend enough time on Wolfram Alpha, you realize it might be a complicated recipe for whatever it is. Like this thing right here, it's like quantum conductance. All right, G naught, that's the thingy we saw. What are our basic unit dimensions? Mass to the -1, length to the -2, time to the 3, current to the. Now, remember, I said charge. This is current. Current happens to actually be something you can kind of derive from. Basically, they're kind of interchangeable, and these things actually arise, which was very interesting when I first saw the tail end of this equation. Took me a while to figure out. This is basically the inversion boundary, because we're basing this geometry off of what's known as like the hyperbolic figure 8 knot. So one of our primary constructing factors right there. The numbers seem to just keep popping up when Thad was initially going through this. He's like, what the heck is this thing? He kept on getting this thing. It's figure 8 knot hyperbolic volume. It's like, what the heck is this? And then you realize that's a double cover. So basically, you have something going around so it can persist. I kind of view it kind of like a Rasengan from Naruto. Basically, just an energy contorting all around like that. Um, and we actually know its geometric properties. It's actually very interesting. It's complex, but it's based upon more simple rule sets, which is interesting. But basically, the whole point of this is when you put the. Oh, let's just put it in right now. All right. Here's the interesting thing. So we get blank mass times the Planck length. So elementary mass, elementary length, and then Planck charge squared, but we wanted the denominator, so we'll do -2. Okay. The interesting thing that, and we need to do multiplication because it's going to give us a list. Okay. Okay. We see Planck mass, Planck length per Planck electric charge squared. Happens to come out to a number that's 10 to the -7. Huh. Because what you notice is as you go through these different constants and stuff, right around 7 decimal places, it seems to get a little bit hand wavy there. But the whole point of showing you this, okay, we get mass, length, charge. Cool. Look at our dimensions. Mass, length, wait, time pops out there, and we get current too. Where did time come from? Because charge seems to be a factor of time. So yeah, you can break up charge into time and current. That seems to be very interesting. But we go back to our friend over here. Okay. So this thing over here that's a Zhou1 squared, and we divide that by pi, because who doesn't like pi? And what the heck is a Zhou1? We go to our friend the hyperbolic vortex equation. This is linked in the doobly-doo here. All right, this is a Zhou1. This is the first answer. We literally just take that, we plug it in. Oh, go back over. Okay, Zhou1 squared equates to what we colloquially know as the fine structure constant. That whole 1 over 137.035999, yada yada yada. So this is our action. We've got fine structure constant divided by pi. The constant we use to help define what the heck a circle is. I like circles. And we multiply that by our dimensional ingredients, our boundary conditions. So Planck time, Planck charge squared, divided by the Planck length squared times the Planck mass. Okay, and we have, this is our terminal action. This is why we have that inversion of about 10 to the negative 7 there, because very interesting articulations seem to happen. So that is 1 plus, in this case, it happens to be minus because this is a negative factor. We subtract out, what is this? The square root of zeta of 3 times just theta squared. What the heck is this stuff? What the heck is the Riemann zeta function in here? Okay. For noobs like me, we go to our friend Wikipedia again. The Riemann zeta function, or Euler-Riemann zeta function. Euler. I noticed a lot of things. I don't know if the Greek letter zeta is a mathematical function of a complex variable defined as the infinite series of n equals 1. In this case, this is basically zeta of s is how we express it. We see that little squiggly thingy there, that z, and then we have s. Okay, basically it's 1 over 1, 2. Basically, we kind of go through the integers there, and then it's raised to whatever power that is. Okay. The Riemann zeta function plays a pivotal role in analytical number theory and has applications in physics, probability theory, and statistics. Euler, of course, basically talked about a lot of this stuff, so that's awesome one. 3 plus 1 equals squirrel. I don't think that's an untrue statement. Welcome, Whitechapel. Thank you for joining. We're just discussing the finer points of squirrel persistence. Again, probably not an untrue statement. Okay, where are we going to? And that was a zeta of 3. Okay. We'll just go through this. It's just a little tidbit. This doesn't really have anything to do. Just get the old noggin a jogging. The values of the Riemann zeta function at ease of even positive integers were computed by Euler, because of course it's Euler. The first of them, zeta of 2, provides a solution to the Basel problem. Isn't that the thing with the lighthouses and stuff? Concerning an infinite sum of inverse squares. Okay, so another math thing. In 1979, Roger Apert proved the irrationality of zeta of 3. The sum of the reciprocals of positive cubes. Oh, very cool. Okay, so that's what we got there. So just a little thing for the noggin, get a jogging. Okay, so we got 1 minus the square root of zeta of 3 times j r theta times that inversion boundary, that 10 to the negative 7 there. What the heck is j theta? Go back to our friend the hyperbolic vortex equation again. Links in the doobly-doo. Okay, what's the j theta? Let's reload real quick. So if we go down here, our first two answers, they just happen to be straight numbers there. Okay, so that's essentially, it's a one-dimensional answer. We go to the complex. Why? Because they're two-dimensional answers. See, they get additional components. And then what we do is, oh god, I'm sorry for jarring you all. We swap from Cartesian form to our trigonometric form. Okay. Since my Wolfram alpha displays the other way, we take this right here, or basically this magnitude here. In this case, the positive one. And then we square it. And when we do all that, we throw it in to our friend Wolfram alpha here. And we get this. So again, this is that J1 squared divided by pi that we see over there. Cool. I actually kind of like the way Wolfram Alpha put this one out, because now we got the boundary conditions right there. So Planck time, and that's the Planck charge squared, divided by the Planck length squared, times the Planck mass. So you can see that, time, charge squared, length squared, mass. Cool. We go to our terminal action there. Again, this 1 minus the square root of zeta of 3 times that number we had over there, that j theta squared, and it's 10 to the negative 7, so we just, notation-wise, divide by 10 to the 7. And we come up with this number here. This number we're looking for. -5. Oh, I'm not used to this. I'm used to seeing the powers displayed for me. I got to actually look and do some thinking. Okay, so what I learned in basic maths in school is we move the decimal place over by 5. So we go 1, 2, 3, 4, 5. So that will be our first number over here. What are we looking for in IST? The number we're looking for is 7.748. Okay. So 7.748, 091, 091, 729. And that's being defined as exact to the best level of our measurements and devices at this time. So 729. 729. Oh, the next digit's a 2. So if we were to round down, my friends, this appears to be a geometric derivation of the quantum of conductance. Excuse me, the conductance quantum. Which one? The conductance quantum. Of that one. Hey, welcome, Fractal Automata. Thank you for joining here. Yes, yes. Exactly. What the nerve am I doing? Yes, as a crazy person on the internet has had the benefit of talking with a whole lot of really smart people. Uh, some of whom are probably actually watching now or temporally in the future. All I know is, hey, it's at least a story. Is it right? I don't know. I guess we're going to have to wait for all those great experimentalists to come back with some observations. Maybe get an additional significant digit or two. Why? Because we can. Humanity's pretty awesome. That, and I'm pretty sure we need a win right now, at least in my opinion. But that's all we got. Peace out. Take care of yourselves, everyone. It's a wacky and wild world out there, but I got hope. I believe in it.